Hamming distance problem. Let me remind you what is the Hamming distance. In this example, we compare the two lists, and if the elements at a certain index are different, we say we have a distance of 1. In this example, the source is different from the target by 4. But if we allow to swap some of the elements, in this example, 1, 0, the story becomes we swap 1, 2, which becomes 2, 1, then the distance can be reduced to 0. And the 2, 3, we swap the other two elements, it becomes 4, 3, then the distance becomes 4 equals to 4, distance is 0. 3 is different from 5, the distance is 1. So we say after swapping, the distance between the source and the target is 1. If we can swap, then it becomes a unified problem. Why do I say that? It's because in this example, we notice that the 4 swap orders covers all the index from 0 to 4, which, if I remind you of the bubble sorting, you know that if we are allowed to swap the neighbors, then we can rearrange the list in any order, which is the same. So for any element in this set, if we are allowed to swap them, then we can rearrange a subset of the array into any order. If we have in the subset, we have the ones which is same to the target, then the Hamming distance can be reduced. Let us rewrite in the Java. We know we need to use the union find, right? So we write a union and find algorithm. I remind you that in the union find problem, we have the concept of the parent. In this example, we have the in the very beginning, all the parents point to themselves. That's it. Later on, we say that if x is different from the parent, we continue looking for it. Finally, we can return this. Once we have the find, it's easy for us to solve this union problem. So first we find the parent of x. It's this one, and also the parent of y. We can find it using this. And if they are different, we do something like we can either give the we assign them with the same parent. Yeah, then we make the union of all of them. And finally, we have to loop through it again. It's because we have to guarantee that they are all the same. Finally, we have a list of the elements. Like for example, we have, let's say, the index like this, but their parents are like 0, 0, 0, and 3, 3. In this case, we want to group the 0, 1, 2 into one set and 3, 4 into another set. We can initialize it like this. Use a two-dimensional array to replace the hashes because the index is it's small. My hash, yeah, we can do like this. And for all of them, we loop. And finally, we get a list. And we see that if one before, we have to know that who are in this swap large set. So we need the data type, the hash set. Oh, I have to use the integer. Then we know who are in there. So if I using that function is in the my set, then we add it to the my hash. Oh, sorry. This one is different. I have to append it. Well, my hash. Well, it's better to call my hash like this. We put it here. New hash set. And then we should, when we get the parent of I, we wanted to add I to it. And that's it. And also for, once we have the my hash, it's like, for example, 0, we point to 0, 1, 2, and for 3, it points to 3, 4. Later on, maybe we stop by here, and we wanna see how the parent and the hash is like. Sorry, my hash, we do not see my hash, but we definitely see how the parent is like. Oh, sorry, my bad. It's not easy to visualize, but anyway, we know that, right? Yeah, that's the what we can do. I'll get back to that later and think about how the hash code works. Yeah, this is a good example. Well, we ignore the printing. Now, once we have the set, we will tell if possible that we, in here we do not have the some elements are not in the swap list, right? Like 2, I can totally ignore it. And later on, I have to tell, say, for the elements, if they are the same, so for each in the hash map, I can do like this. Okay, now these are the hash set. For each of them, we do something. We have the array list. And also the array list too. So for each of the elements in this case, let's see what we do. For each of the index, we have to add it. And if then we have them added. We know that the list in 1 and 2, they are in the same group. What? Anyway, I don't care about the order. Let's see how they're defined. Comparable. Oh my. They cannot be compared. Okay, I forgot how to sort it. Collection sort. Once we have the sort, then it's easy to compare. We just say compare sorted. Oh, their list, sorry. Is a get. So here I counted same. If they are the same, I increase it. Else, if A it's smaller, then I should increase, right? Otherwise, the J should increase. That's it. Later on, what we returned are just the Hamming distance of two sorted. Cannot compare. Well, okay. Equals greater. Well, you're right. It's I have to do like this. They are integers. So for if they're the same, then it's possible to compare. However, if they're not, then that is not easy. Maybe I should simply convert them into the int. Yes, if the int values are same, then it's easy to compare. Once we have the Hamming distance, we can just add them, and also add the ones that is not in the large group. Well, if I map, then that's a different story. I can simply calculate them. When I reduce what I can do, I need an accumulator. Let's see what we can do. Then we loop through the ones that is not in the superset again. You only compare those are not. And if the ones that we got are different, we know we have to add it by 1, right? And that's it. Let's see what's the result. I see, I have to compare. And I say if it's null, then there's no point to calculate, we just return.